You ever get that feeling when you're staring at a physics problem and you're just absolutely convinced there's a typo? Like there's no way you can solve it with the information they give you. Well, it happens all the time, and it's usually a trap. Today, we're going to see that the solution isn't about finding a missing number. It's about finding a whole new way to look at the problem itself.
So yeah, how do you do it? How do you crack the case when a crucial clue just isn't there? Well, today we're going to put on our detective hats. We're going to solve a classic problem that, I promise you, looks completely impossible at first glance. All right, here is our case file. It's problem 1.122 from the legendary Irodov physics collection. Here's the setup. A little disk starts from a dead stop, slides down a 30-degree incline. Then it hits a flat, horizontal plane, slides for 50 centimeters, and stops again. We know the mass, the angle, that horizontal distance, and the friction coefficient. Our mission? Find the total work done by friction over the entire journey. Now, right away, your brain probably goes, wait a minute. To calculate the work done by friction on that ramp, you need to know how long the ramp is, but they don't tell you. And this, right here, is exactly where most people get stuck. It is a classic trap, and it's designed to make you just give up.
But we are not going to fall for it. Instead of getting bogged down by one missing detail in one part of the story, let's zoom out. Let's look at the entire trip, from the very beginning to the very end. This big picture view lets us use a much, much more powerful tool. And that tool is the work-energy theorem. You know, this is one of the most beautiful and elegant ideas in all of mechanics. All it says is that the total work done on an object, by all the forces combined, is simply equal to its change in kinetic energy. This is our master key. So let's use this master key on the disk's entire trip. What's its kinetic energy at the start? Well, it starts from rest, so 0. What's its kinetic energy at the very end? Well, it stops, so that's also 0. That means the total change in kinetic energy, from start to finish, is a big fat 0. Nothing. And here is the beautiful part. If the change in kinetic energy is 0, the work-energy theorem tells us that the total work done by all the forces acting on our little disk has to also be 0. Everything has to perfectly balance out. Okay, so who are the players here? Which forces are actually doing any work? Well, there are really only two. You've got gravity and you've got friction. Gravity is doing positive work. It's pulling the disk down, trying to speed it up, giving it energy. And friction is doing negative work. It's fighting the motion the whole time, taking that energy away. And we now know their grand total has to be 0. This leads us to this incredibly simple, incredibly powerful idea. The work done by friction has to be the exact negative of the work done by gravity. That's it. This one insight completely changes the problem. Suddenly, we don't care about the length of the incline at all. If we can just find the work done by gravity, we just flip the sign, and we've got our answer. Okay, piece of cake, right? The work done by gravity is just mgh, mass times g times the vertical height h the disk dropped. But wait a second, we've got another missing clue. The problem doesn't give us the height. Oh man, it feels like we just traded one unknown for another. Or did we? This is where the detective work gets really clever. Instead of working forwards from the start, let's go to the end of the story and work backwards. It turns out the disk's final moments on that flat surface hold the key to everything. Let's just focus on that horizontal part. We'll apply our theorem again. The final kinetic energy here is 0 because it stops. So the change in energy is caused entirely by the negative work done by friction. And we can actually calculate that work. It's just negative the friction coefficient, mu k, times the normal force, which is just mg on a flat surface, times the distance, L. So we plug in the numbers, the 0.15 for k, the 50 grams for mass, and so on, and we find that the work done by friction on that flat part was negative 0.037 joules. Now here's the crucial point. This number tells us exactly how much kinetic energy the disk lost on that flat section. And if it lost that much energy to come to a stop, it means the disk must have had positive 0.037 joules of kinetic energy the very instant it hit the bottom of the ramp. We did it! We found our critical piece of evidence by working backwards from the scene of the crime. So now, armed with this brand new piece of information, we can go back to the first part of the mystery, the slide down the incline, because now we know exactly how much kinetic energy it had at the bottom. On the incline, the disk went from 0 energy to 0.037 joules.
Where did that energy come from? Well, it's the result of a battle. The positive work from gravity, which is mgh, minus the negative work done by friction on the ramp. And with a little bit of trigonometry, we can express that friction work in terms of h as well. This lets us build one single equation where h is the only thing we don't know.
And when we solve that equation for h, there it is. The initial height was 0.101 meters, or just about 10 centimeters. That was the missing clue we needed from the very beginning. Case cracked. Seriously, the hard part is over. Now that we know the height, we can finally figure out the total work that gravity did. And once we have that, we are literally one step away from the final answer. The work done by gravity is just mgh. We plug in our numbers, and it comes out to positive 0.050 joules. This is the total amount of potential energy the disk started with, all of which eventually got turned into motion, and then lost to friction. And now, all we have to do is remember our master key, that big picture idea that made this whole thing possible in the first place. The total work done by friction must be the exact opposite of the work done by gravity. So the final answer is negative 0.050 joules. And we did it. We solved the whole thing without ever needing to know the length of that incline. How cool is that?
So what's the big takeaway here? This isn't just about one problem. It's a whole new strategy for you. First, always look for that big picture shortcut, like a conservation law or the work energy theorem. Then figure out what the real missing clue is. And if you get stuck, don't be afraid to work backwards from the end. Use one part of the problem to unlock a different part. This is a mental tool you can use over and over again.
And that kind of leaves us with a final question, right? What other problems, maybe not even in physics, seem impossible because of one missing detail, but could be totally cracked open if you just took a step back and looked at the whole picture first? Something to think about. Thanks for tuning in.